Now we're going to look at a problem of an object sliding down a frictionless inclined plane. Suppose a toboggan loaded with the vacationing students' total weight W and slides down a long snow-covered slope. So here's the slope. The hill slopes at a constant angle alpha here, and the toboggan is so well waxed that there is virtually no friction. We want to find what is the toboggan's acceleration and the magnitude of the normal force N the hill exerts on the toboggan. So we know the total weight is W, and we want to find out, we also know what is the alpha, and we want to find out what is the acceleration and normal force. Well, if you're wondering where the numbers in this problem, well, the numbers are not given, but we know that the weight is given and we know the alpha is given to us. So our answers for acceleration and normal force has to be represented by W and alpha. Okay, so to find the acceleration, we know that it is related to the forces. It is caused by the forces. Therefore, force and acceleration relationship is given to us. It's known to us from Newton's second law, and we know that the forces, sum of the forces, equals mass times acceleration. Now, we have to look at the toboggan with the loaded students as a one whole object, because we know the weight, and we know that the weight of this system is always downwards. So I'm going to draw weight downwards. And we know that the incline, the hill is exerting a normal force on it. Okay, so there are the two forces only acting on that toboggan with the loaded students. Let's draw a free body diagram. For that, we need to define our axis. As I mentioned earlier, it is convenient to use tilted axis for the inclined planes, and it is always convenient to use your x-axis to be parallel to the incline. And the experience shows that it is also convenient to use positive x-axis to the direction of the motion. So that's why I used positive x going downwards, and then make a perpendicular line that would be your y-axis. I'm going to keep the y positive up and negative y down. Now our forces, the weight, actually our toboggan, we're going to put on the, as a particle on the origin. That's my object. And then the forces that act on it is the weight and the normal force. The weight is always perpendicular downwards. And the normal force is perpendicular to the surface, therefore perpendicular to the x-axis. So it has to be right here. So the normal force. And then we have the system is accelerating downwards. In a free body diagram, we always draw this to make sure that the direction of acceleration is known when you write your Newton's second law. Now all I need to do make this vector equation into scalar equation. So, or component equation. So let's write this as a sum of the forces by x equals max. Sum of the forces by y equals may. And there is no motion on the y-axis, so this should equal to 0. And the motion on the x-axis, ax is the a, so I'm going to write ma. When I say m is the mass of the combined mass of the toboggan with the students. Now, let's let's find what are the forces that are on the x-axis. I'm going back to my free body diagram, and I see that I have a force, the weight, that needs to be resolved into components. But then also let's identify what's our angle. This is alpha, and the weight could be resolved into x component. So weight x, and then weight y. And then I don't need this anymore. Let's immediately do what is the weight x component equals to. As you can see, this is the weight x, and it's opposite to the angle alpha. So I can say weight x equals weight times sine alpha, and weight y equals weight times cosine alpha. Now let's go back to our Newton's second laws and see on the x-axis we have only the weight on the x direction, which is weight sine alpha. Let me just write weight x first. Weight x component equals ma x. All done. We already decided that a and ax are the same. This, if I plug it in the expression for wx, that would be w sine alpha equals ma. Now, same thing we'll do for y component. I have a normal force going upwards minus wy, that equals that equals 0. From here, I can say normal equals wy, which equals w cosine alpha. So it seems like we solved. We have an answer for normal now. Okay, now for the acceleration, there is a problem. We need to find the mass. Okay, for that, I'm gonna rewrite this again. Weight sine alpha equals ma. To find the mass, I know that the weight equals mg. And from here, I can find mass equals weight over g. So if I plug that in, I will get weight sine alpha equals weight over g times a. Weights will cancel out, and then I will end up having acceleration equals g sine alpha. Here's another answer to us, for us. But we got a very interesting result for acceleration. The mass m does not appear in this expression for acceleration. This means that any toboggan, regardless of its mass or number of passengers in it, slides down a frictionless hill with an acceleration of g sine theta, sine alpha. In particular, let's look when alpha is 0. When alpha equals 0, what do we have? We have a flat surface with no slope. The acceleration becomes a 0, as we should expect. Toboggan would not slide. When the surface is vertical, which means alpha equals 90 degrees, we end up having sine 90 is 1. We end up having acceleration is g. It's a free fall, which we would expect. Now, let's see what we can say about the normal force. Let's notice that the magnitude of the normal force exerted on the toboggan by the surface of the heel is the weight cosine alpha, or mg cosine alpha, which is proportional to the magnitude of the weight of the toboggan's weight. The two are not equal, except in the special case where alpha equals 0. So for you, I want you to take away a question. Try to solve or practice or think of a practice problem as this. So I'm going to write practice problem for you to do. So at what angle does the heel slope if the acceleration is half of the g? At what angle does the heel slope if the acceleration equals half of the g? Well, you should, when you solve this, you should get an answer 30 degrees. Have fun and stay tuned for more to come.